Здравствуйте, дорогие товарищи. Всем большой привет из Calgary. Hello, everyone. Best regards from Calgary, Alberta, Canada. Thanks for coming. Today, we will discuss modeling of environmental constraints in capital projects. As a matter of fact, I did a similar presentation last year. It was about risk quantification in complex projects. This year, Alex Sidorenko asked me about a presentation related in a way to environmental protection. So in a way, this presentation is a spin-off from my previous one, and we will discuss weather and closure calendars related to environmental constraints. And as usual, we need to quantify individual risks, including environmental ones. We need to factor teams' witnesses to individual risks, including environmental risks. And last point is we need to count risk interactions, which would include knock-on and compounding. And the key point here will be that we need to take into account all four factors listed above, because otherwise contingencies will be too optimistic. And we will build a couple of, actually three models in order to demonstrate what happens if some of those factors are not taken into account. My presentation is based on my previous PRM experience in quite a few large and mega projects with combined budget of more than $150 billion. And this experience is recapped in a couple of books published by Oxford University Press and John Wiley and Sons. Although writing is not the primary purpose for me, because I just try to share my experience. Some other authors do the opposite. They write books without proper project experience and try to show some shortcomings of risk management. And basically, finally, they might find themselves in a situation where they have employment problems because project people, they don't like skills related to high horse riding or muddying the waters. So anyway, my purpose is to show and share with you some life hacks that will allow you to quantify risks in projects properly in order to receive or come up with adequate contingencies. Basically, environmental risks are part of any modern capital project, and that's why actually I have a lot of experience with that with my previous projects, and currently I work on 3 mega projects as a consultant. Everywhere we have environmental angles. So environmental constraints, every country has national environmental protection regulations, and they result in many constraints related to land use, groundwater pollution, species protection, protection of historic, cultural, archaeological sites, and so on. Moreover, it's quite serious business, because in 2020, about 227 people were killed who protected land and environment. Most of them in South America, some in Africa and Philippines, and even in Canada, 1 person was killed. I read a report that 15 species were extinct last year. Another report says it was like 23 or something. But anyway, you see the consequences or what happens when we deal with environmental protection. But we won't go there. We will consider some technical angles of this issue. So many environmental constraints are handled by various project disciplines like engineering, safety, environmental stakeholder management, and so on. Of course, all those risks and issues should be factored into PRM and finally to Monte-Carlo modeling in order to come up with final contingency. But some of those constraints should be handled directly by scheduling and in schedule risk analysis. First of all, I'm talking about weather constraints. They are probabilistic. We can talk about sandstorms, winds, raining, cold and heat waves, I mean excessive events like that above the allowances in existing schedules. Like when I worked in Middle East with Saudi Aramco, sandstorms were almost everywhere in our projects. Even cold weather was part of that. in the northern part of Saudi Arabia. Second point, we need to take into account legally enforced protection constraints. We will call them closure periods. They are deterministic. And we need to take into account existing requirements related to mammal mating seasons, birds nesting, marine breeding. Yeah, I had all of those issues in my previous and even in current projects. I heard also about protection of insects like butterflies in some areas of the world. So when you do projects somewhere abroad, you need to learn quickly what are those constraints. Mathematically speaking, we will mostly talk about deterministic constraints, legally enforced protection constraints in our sample models, and those constraints are equal or similar to conditional branching. And actually, the regular constraints like start on, finish on of those periods, they don't work because they just distort modeling and they are not applicable to schedule risk analysis models. We just need to do something differently using different functionality. So purpose of this presentation will be to show how schedule risk analysis works in when we need to take into account legally enforced protected constraints. You can use PERT-master or Oracle Primavera risk analysis. That's what I did. Or you can use Safran Risk. It's a very good tool as well and has similar functionality. Besides legally enforced protection constraints, we need to, as we discussed previously, take into account team's weaknesses. We will call it project delivery subsystem issues. Sometimes they're called systemic issues or whatever, that's better. And they might include environmental related issues, for instance, misunderstanding of regulatory environment requirements, and some unqualified specialists might be involved in this discipline, or just, and as a result, poorly prepared environmental impact assessment reports could be submitted. So if we consider a couple of different projects with similar scopes, we might have different issues and as a result, different environmental risks, same risks with different impacts. After that, we need to take into account risk interactions, as was pointed out previously, and as a result, we will get a nonlinear Monte-Carlo model. So this is a kind of roadmap, what kind of models we will consider. First is just a deterministic schedule without any constraints, without any risks. Then we can add, we can just build a regular Monte-Carlo model as everybody can do. And it will be called linear SRA model in this presentation. So no PDS issues, no risk interactions. On the other hand, we can build the Monte-Carlo model, the linear Monte-Carlo model, through taking into account those environmental constraints. This will be still a linear Monte-Carlo model, but with those constraints, and we will compare results. And finally, we can take into account the systemic risks or PDS issues, and we will take into account risk interactions. And finally, we will get the nonlinear Monte-Carlo model with constraints, and we will compare contingencies for all three of them. The difference will be quite significant. So a bit of theory. There are some empirical studies about overspans, right? And we will be talking about scheduling, but overspans, they have similar situation. So what's happening? First curve with the sharp peak is about estimated project costs, and base estimate, which correspond to number one ratio, actually one. This is without contingency and just deterministic number. It turned out that the most popular contingency, it's a difference between this line and one, is 7% only. And that's called probable 7% syndrome in risk management when contingency is too small. And the reality of this second dotted curve, right, it shows that the results differ drastically from this estimating curve. And we can call this difference conditionally systemic error of risk estimating or contingency estimating methods. And this delta or systemic error will be in our focus for in next couple of slides. So theory in terms of systemic and random errors is shown by those four quadrants. We might have very high accuracy of estimates, right? But we can have low precision and vice versa. So delta, this systemic error of estimating, shows that in those two cases, delta is so big that actually the curves we receive from our Monte-Carlo or any other analysis won't cover the actual outcome of the project. Here we have a better situation when the curve actually covers the actual outcome. Yeah, and why the curve or bigger random error is good error. It's just the width of the distribution, and it reflects on risk exposure of a given project. So we need to understand why methods, Monte-Carlo methods in this case, why those methods might have quite big delta. And in Monte-Carlo methods, the reasons for high deltas are some missed or mishandled factors that are used as inputs to Monte-Carlo modeling. Yeah, once again, constraints we discussed previously, if they are not taken into account, modeling won't be adequate. Uncertain risk events, we need to take them into account properly and just identify the right environmental risks. But those risks should be modified due to psychological bias or organizational bias. And this is about team's weaknesses. And finally, all identified risks, including environmental risks, should be considered in terms of their interactions. It's knock-on and compounding. If one of those factors or two or more factors are missed out, we will get a very optimistic contingency, and we will see the models to understand why it's happening. This is a summary table. It's actually from my previous presentation that shows that the different types of Monte-Carlo, from range estimating and line item arranging to nonlinear integrated schedule and cost risk analysis methodology, they have different issues with taking into account the relevant risk factors. Depends here means you can include or you might not include those constraints as calendars to your schedule models. And of course, we are not considering here cost risk analysis or integrated cost and schedule risk analysis. It's outside of the scope of this presentation. Basically, we will compare a linear schedule risk analysis model, LSRA, with nonlinear SRA with and without constraints as calendars. Okay, model number one, a very simple situation. We just have a sample schedule, few activities, and we have 6 risks from risk 1 to risk 6. One of them overlooked external stakeholders' requirement. Requirements might be treated as environmentally related risk, and there are some other risk engineering errors and omissions, poorly executed work in construction, and so on. It doesn't matter in a way. We are talking about mechanics, how it works, whatever the risks are. And among them, there might be environmental risks. So duration here, we have like 13,000 days, 1,300 days, 6 non-interacting risks. And the result of that modeling, everybody can probably build this model. We need to map, of course, those risks to impacted normal tasks, so same stuff. And yes, we included general uncertainties here, it doesn't matter. So the contingency for that sample linear SRA model is 13%. It's not a lot, but that's what we got from that model. And that's usually what's happening in our modeling practice. Now, besides the same risks and the same schedule, let's add closure periods from March 1st to August 15th. Actually, this corresponds, as I remember, to crab closures in offshore projects in North America, in some places, of course. So if we add those constraints, we will get this result. As you see, there are some breaks in the curve, which is normal for constraints of the kind. And the contingency in this case, just because we added those closure periods, will be 22%, which is actually expected. So instead of 13%, it will be 22%. And next is most difficult part of my presentation. Now we need to consider complexity of this project. So we need to consider how risk interactions will change that contingency and how team's weaknesses will do the same. So let's review theory a little bit. So structural complexity usually is about number of project parts, packages, interfaces, locations, stakeholders, and so on, and type and intensity of parts interactions. Literature tells us about pooled interactions, sequential interactions, and reciprocal interactions. Pooled, it means it's about internal interaction inside standalone parts. Sequential, it's about relations among the parts when there are input and output relations among the parts. And reciprocal is about combining when there is mutual impact of parts on each other. So here we will have internal risk amplification due to team's weaknesses, analog of that, right? Here we will get knock-on interactions, and here we will consider combining interactions, which is the reciprocal interaction, actually, right? And there will be several, actually not several, 3 types of projects: simple, complicated, and complex. And chaotic is a spin-off from complex when kind of situation, the control is lost in a complex project. Last year, I showed how a complex project become chaotic. There is a Monte-Carlo theory behind that. You can review my previous presentation. It's quite interesting topic. So now we need to talk about 2 subsystems of any capital project. It's about structural and delivery complexity. First first subsystem is project structure subsystem. Actually, what should be delivered? Parts, again, what kind of packages we have, interactions, location, and so on. And second part is about delivery subsystem, or PDS, it's called in this presentation and in my book. It's about quality of procedures and consistency of their implementation, mostly. It's about bias, it's the same topic. So there might be a mismatch between PDS and PSS, as showed here, right? And we have differentiation of project parts angle. We have interdependencies of parts or parts interactions. And here, in terms of PDS or delivery, adapted procedures and procedure implementations. There is a right part of that chart that shows all the details, but I cut it off for simplicity purposes. You can read it in my book if you are interested. So that mismatch, PSS and PDS mismatch, there are 3 questions we need to think about. So is the project team up to the challenge? Is it strong enough in terms of people, procedures, and their implementation to deliver this project as represented by project structure subsystem? So is the project system mature enough? And is a mismatch static or dynamic? Actually, it might be either. So this mismatch could be static, and it relates to chronic project system issues, again, team's weaknesses. Dynamic part of this mismatch may happen when some risks occur and they start interacting. It's dynamic part of the mismatch. So when risks happen, it's about dynamic part. They propagate due to parts interactions. And again, we have three types of interactions now. One is internal amplification of standalone risks, it's static PSS, PDS mismatch. Another one is a knock-on interaction, which is about input-output relations among the risks. And compounding is also a dynamic type of mismatch when some risk happens simultaneously. Yeah, there are some examples. You can read them. Chronic issues given when project team is lacking experienced process engineers, to say in refinery project, and they will exacerbate, amplify any given engineering risk. Any risk in this particular project will have bigger consequences than in another project, to say. Knock-on interactions, to say we have errors and emissions, is risk number one in this situation. And risk number two would be startup failure risks. And of course, if you have some errors and emission at the beginning of the project in engineering, startup risk or risks might be exacerbated significantly. Compounding is about errors and emissions in engineering when they happen simultaneously with missed external stakeholder requirements, which might be about environmental requirements. Yeah, we can come up with medical examples. So we are not, some of us are doctors, but medical doctors. So it might be about COVID, underlying conditions, another disease, postponed consequences. It's not very funny example, but it's our life now. But you can think about what might be static or dynamic PDS, PSS mismatch in this situation, but I won't go there. So my first attempt to calculate deltas or systematic errors in Monte-Carlo models was done in San Diego, actually, at the AACE conference in 2018. So actually, I just used one simple parameter, beta, which is kind of nonlinear parameter when you have every particular risk multiplied by 1 plus beta, a product with R, with the same risk. So in a way, it's about team weaknesses. No interactions among risks. Every particular standalone risk will be modified. And this modifier showed perfect kind of results in terms of comparison to, you remember with the previous chart, when you have a sharp peak estimating, right, when beta is 0, basically, it's linear model. And then you have that fat tail curve, which corresponds to a weak team. But that was only the beginning, because we need to think about risk interactions as well, not just pooled interactions as here. But let's start with static PSS, PDS mismatch. That's exactly the situation when there are some causes related to team weaknesses. Now we can call them PSS, PDS static mismatches, chronic issues, team weaknesses, or systemic risks. They have, it looks like they have a power to modify non-linearly schedule and cost impacts in combination with some other causes. And we have the beta parameter as internal amplification parameter. It's non-linear parameter. Then we need to talk about previously spoken about knock-on PSS, PDS mismatch interaction. To say risk one happens in engineering, there would be quality issue, and that quality issue will be discovered only in construction, to say, right? This is because of that dynamic new cause D, right? The risk to consequences in terms of cost and schedule will be much bigger than if that would be a standalone risk. Now we have a cross interaction. Risk two modifies, actually risk one modifies risk one, two, and we have that formula. When the beta to one parameter, it's knock-on parameter, which modifies consequences for risk two. And last type of interaction is compounding. And here we have cross interactions, but two equal risks R1 and R2, they might happen simultaneously, which should be shown to say in the schedule when you see that two risks might happen at the same period of time. And due to amplification, compounding parameter will lead to a situation when the sum of risk 1 and risk 2 would be much bigger. It will be nonlinear expression here, right? Now we need to discuss how we should identify those interactions. Here we are talking about only cross interactions, not internal interactions, because they're internal for particular standalone risks. Here we will discuss knock-on and compounding only. So if you have the regular project schedule, you have some mapped risks, as we usually do, right? Then you need to identify what kind of interactions we need to think about. So risk 1 and risk 2 will modify risk 3 because they will happen simultaneously. But risk 3 will modify risk 4, which is actually construction, I believe, or startup. And this is knock-on. This is compounding those clouds, right? And those lines are about knock-on interactions. So part of that chart is just regular, but now we need to quantify all those compounding and knock-on interactions. And we saw the formulas already. We need to modify our risk register that we use for Monte-Carlo modeling. So every risk, standalone risk, should be replaced by this expression, and every instance of knock-on interaction should be replaced by this nonlinear expression. And in case of compounding, we have another expression. So everything could be done in Microsoft Excel spreadsheet, in the Excel, which kind of describes the risk register, right? Or keeps the risk register used for Monte-Carlo. You just need to kind of use those formulas. How to do that, it's technicalities, you can read it in my book. But we need to understand what kind of parameters beta should be used. And for that, we need to do first qualitative evaluation of PSS, PDS mismatches. And after that, we will consider quantitative kind of calibration of them. So as we discussed, first part is about PSS, or project structure subsystem. And there are a number of parts, there are a number of risk interactions, and we have complex projects, we have complicated projects, and we have simple projects, according to previous discussion. On the other hand, project delivery subsystem, PDS, it has parameters like quality of procedures and procedures implementation. So we have also three situations when this PDS is weak, or passable, acceptable, or quite robust. Now we need to merge this and kind of structural and delivery complexity. And here we are talking about already about maturity of the entire project system. And the project system, which consists of two subsystems, right, might be immature, ordinary, kind of acceptable, and mature, quite robust. So calibration should be done after that. It's already a quantifiable exercise in order to understand what betas are. The betas correspond to those three categories: immature, ordinary, and mature. Yeah, you can come up with kind of dividers. What does it mean mature system? What does it mean ordinary system or immature system? It means the additions to your linear Monte-Carlo models. If the system is quite mature, it means no interactions, internal risk amplification is low, and the addition will be just, I would say, below 10%, maybe 5% if you wish. Ordinally might be qualified as 10 to 25%, and immature more than 25%, but everything depends on risk appetites of a particular project. I usually use those numbers. Yeah, we are talking about schedule slippage only. Cost overrun might be do the same way. After that, you put the same dividers, same baiters to your model, run it several times, and then you will pin down parameters baiter that will correspond to divisions, dividers between weak and medium and strong situations for a project system. And when you know that, then you can discuss the particular parameters baiter for particular dividers, for particular mature or ordinary or immature system inside of those ranges. So if we build this model, and I did that before this presentation, you still have the same 6 internally amplified and interacting risks. You have the same closure periods as in previous model, right? And the result will be quite amazing because you will have several closure periods here, right? And actually P70 in this situation, it's here, P70 will correspond to contingency 50%. And that's quite big increase. And this demonstrates what happens when you take into account both closure periods and team weaknesses along with risk interactions. If you miss one of those parameters or factors, you will have quite optimistic contingency. This is a summary of the modeling exercise, 3 models, linear, SRA with and without environmental constraints, and nonlinear Monte-Carlo model. So those are numbers we just discussed, contingency numbers. And as you see, P70 increased in 3.8 times. So all 3 factors should be taken into account in their combination in SRA models. Same thing might be done for cost and schedule risk analysis, but it's outside of the scope of this presentation. Some conclusions. Actually, it's preposterous to expect adequate risk quantification if a selected risk quantification method is inadequate. It means when systematic errors are flourishing. So it means that it might be quite misleading if you have those 13 or even 22% contingency when you don't consider nonlinear effects of risk interactions, including environmental interactions. So we need to take into account constraints and team weaknesses and interactions of risks. By the way, the linear Monte-Carlo models still can be used, but you need to be sure that your model, your project is quite mature. It means there is a very small PSS-PDS mismatch. I have an example of that. I used to work for a company called Shell, and we did one project in Alberta where government was very interested in environmental aspects of the project. It was CO2 sequestration, and the team was quite strong, and we didn't have much issues. If we had them, government supported us in resolving them. So I used the linear Monte-Carlo model, schedule and cost analysis model, and actually P50 number was very close to real completion date of the project. Actually, it was P42, I believe. It means that if a project is very strong, a robust system of project delivery, no mismatch, you still can use the linear Monte-Carlo model. But that's exactly what we considered in this presentation when betas are low, closer to 0, right? It's just a linear model. Another point is about politics. You probably know that it's very difficult to honestly discuss team's weaknesses. Everybody believes that a particular project team is quite so strong that there are no PSS or PDS mismatches at all. And I call this, by this reason, Monte-Carlo modeling a branch of political mathematics. I come across that quite often. I believe you, as my colleagues, probably have the same experience. So the role of company boards of directors or third-party reviewers is to establish and implement policies and procedures to keep political mathematics at bay in order to predict adequately the project outcomes in terms of cost and actually and schedule contingencies as well. But that's quite difficult because of bias. Political mathematics is another realization of bias in projects. So this is the end of my presentation. Thanks for attending. And if you have any questions or if you need any PRM service support, just send me a note to my email address and I would be glad to discuss everything with you later. Thanks. Bye-bye.